At the base of the Great Pyramid, the stone seems to stretch into the sky as a singular vertical mass. For 4,000 years, this was the tallest man-made structure on Earth. It is a solid mountain composed of over 2 million individual limestone and granite blocks, with each one weighing an average of 2.5 tons. When this was built during the Bronze Age, workers had no access to diesel engines, iron tools, or even the wheel. There were no cranes to lift the stones, and no pulleys to redirect the weight. This technological gap challenges our modern understanding of construction. Without an obvious mechanical explanation, many observers have filled the void with theories of levitation or external intervention. But the actual physics used on the Giza Plateau provide a grounded explanation for how the Egyptians manipulated their environment using only human muscle and Bronze Age tools. The first obstacle was the terrain itself. To build a structure that stands 480 feet high, the foundation must be perfectly level. The builders had to flatten a 13-acre section of desert bedrock without spirit levels or lasers. They began by carving a grid of shallow, connected trenches directly into the uneven surface of the site. By flooding these trenches, water provided a perfectly horizontal reference point. Workers chiseled away the remaining rock islands until flush with the water's edge, leaving a perfectly flat stone platform. This technique was so effective that the entire base of the Great Pyramid deviates from a true flat plane by less than an inch. Once the foundation was set, the engineers had to transport millions of stones from distant quarries without the use of carts. This temple carving illustrates their primary transport method: teams of laborers using ropes to haul heavy wooden sledges. Dragging a 2.5-ton sledge across dry sand is physically exhausting. As the sledge moves, sand grains pile up in front of the runners, creating a berm that increases resistance until the sledge is pinned in place. Pouring a precise amount of water directly in front of the sledge creates capillary bridges, locking the sand grains into a solid surface. This wet sand cuts the required pulling force in half, allowing smaller teams to move massive loads. Controlling the physics of the sand at a microscopic level was the mechanical key to manipulating the landscape at a macroscopic scale. The final challenge was height. As the pyramid grew, workers had to lift these massive blocks hundreds of feet into the air. A straight external ramp would require more material than the pyramid itself. Instead, builders likely used an internal spiraling tunnel system, hauling sledges up these corridors and using open corners to pivot the blocks 90 degrees. By integrating the ramp into the structure, the pyramid swallowed the evidence of its own construction, hiding the solution within its walls. Looking at the Giza Plateau today, we see the results of these engineering solutions applied at an industrial scale. The site is a physical map of a society that successfully managed the logistical challenges of its environment. Executing these methods across 20 years required the daily coordination of tens of thousands of workers, supported by an agricultural system capable of fueling the project for a generation. The Great Pyramid remains as the final proof that specific mechanical insights, when repeated millions of times, can transform a pile of stone into a permanent monument.